I will introduce this lab and material that is necessary to understand before we can proceed in this experiment. Then I will discuss and introduce the formulas we need for the computational model. Next, I will analyze the motion of my falling object, followed by a discussion of the computational models I developed using GlowScript. For that, I will compare the predicted computational models versus the observed models I have found through Tracker. Then I will end it with the conclusions and reflection section where I talk about some important questions on this topic. In order to understand the motion of a falling object, we first need to understand Newton's second law, which states an object's acceleration depends upon its mass and the force acting on it. Second, we need to understand the forces that are acting on the falling objects, such as gravity and drag. Gravity and drag do not cancel each other. And we also need to understand that unequal opposite forces cause acceleration. To get into formulas, I'd like to address some key assumptions. That the force of gravity is equal to 9.8 times the mass of the object, which in this case was presumed to be about 5 grams. Next, we will assume that gravity is acting in the negative direction and drag is acting in the positive direction. Some important formulas include the velocity update, position update, Newton's second law formula, and the drag force formula. We can see the free body diagram I developed using Microsoft Paint. On the left, we can see that the ball is falling and the velocity has not quite reached its terminal velocity, which is the velocity where the force of the drag equals the force of gravity and they cancel out. The object on the right, however, is representing the object at its terminal velocity, where force of drag and the force of gravity cancel out because they are equal and opposite, therefore leading to a constant velocity. Our new understanding of this material, this is the code I used to develop my computational model. On the left is the code used to create my computational model without drag, and on the right is the code used to create the computational model that includes the drag acting against the force of gravity. The major difference in these two codes is my B value, which is my drag constant. I found this by trial and error until my position versus time graph matched my original model. The Tracker software I used to gather the data and plot my position versus time graph in my real-world experiment of dropping a paper ball. As we discussed previously, the terminal velocity of a falling object is solely dependent on the force of drag equaling the force of gravity and is completely independent of the object's initial velocity. Therefore, an object thrown at a downward angle will not have any effect on the speed of the terminal velocity. As we compare the observed versus predicted graph, I will note that the labeling on the computational models is swapped, meaning the orange line represents the computational model with drag and the blue without drag. The graph clearly shows that the force of drag impacts the position versus time graph and the final position of the object while it falls. Drag works against the acceleration and slows down the object as it is falling. Errors in my data may come from my drag constant being solely derived from trial and error, as well as my falling object being a crumpled piece of paper, leading to ununiform surface area, which may affect the drag on the object.